Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers Doing the Impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind-the-scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. Before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continue to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind-blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuro Approaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical grade system recoveries and educational kits with unicorn hybrid plug for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. Dear NeuroCareers podcast listeners, we're continuing our BCI Award series, and today our guest is Dr. Ben Somers, and he will talk to us about their fascinating project, a brain-computer interface for real-time hearing diagnostics based on EEG response to natural speech. Welcome, Ben. It's a great pleasure to have you on our podcast. Can you please introduce yourself and tell our listeners where you are joining us from? From what part of the world?
Hi, Milena. Thank you for the introduction and for the invitation. I'm very happy to be here. I'm joining in today from Belgium, from Leuven in Europe, and happy to talk to you about our project.
Yeah, thank you. How is the weather today in Leuven? Yes.
In Leuven, yeah. So it's a bit rainy and cloudy today. We had a few nice days, but so far the summer has not been great in Belgium. But yeah, it's okay. It's not too hot, not too cold. It's okay.
Yes, and maybe you can tell our listeners some interesting fact about Leuven. What is it known for? Because through this podcast, we're also talking to people from different parts of the world and learning a little bit about the places that people in Neurotech work.
Leuven, it's maybe a small city that not many people know besides the university. I think the university is the most important aspect about the city. And I think it's one of the oldest universities in Europe. Actually, next year we will celebrate our 600th anniversary. There will be a lot of festivities and art and events and expos. So I think that's something very nice to know about Leuven. But for the rest, yeah, it's there's almost as many students as there is population. So it's really, really a student and university city.
Yeah, that's beautiful. What about the Neurotech program in University of Leuven? When did it start to develop? How does it look like? What are the main branches of it? What is the main focus of Neurotech at the university?
I don't think we have a specific neurotechnology education, but it's very interdisciplinary here in Leuven. There's a lot of collaborations between the university hospital with medical groups and then the electronics departments who do a lot of engineering work and design. Maybe a lot of people also know IMEC, like the chip design company or research center. They're also very involved in neurotechnology. So it's really a lot of interdisciplinary research flowing together here. And I think that's very good for collaboration, makes very interesting research. I myself, I'm an electrical engineer, so I'm also one of those people that flew, that went into the medical sector after my studies because I was really passionate about hearing and about neurotechnology. So yeah, that's how you can see how it goes here in Leuven.
Yes, thank you. And very good that you started speaking about yourself. Can you tell a little bit more? How did you transition from electrical engineering into the neurotechnologies? How did you first learn about this and why specifically work in brain-computer interface with hearing diagnosis? So if you can give us some perspectives on how all this happened.
So I studied electrical engineering here in Leuven. I was very interested by electricity, but I thought it was a bit dry because it had nothing to do with medicine or with living people. So when I started to look into PhD programs after my studies, I met Tom Francard, who would become my promoter. And he had just got a nice grant from the European Union to work on cochlear implants and to make cochlear implants more, cochlear implants are hearing implants that re-enable deaf people to hear. And he got a nice position there to improve sensing capabilities of cochlear implants to sense how well they are performing. And then, I was immediately sold on the project. I thought it was very interesting to make a change for patients. And then I started my PhD here. That took 5 years. And then after my PhD, I rolled into a translational grant, we call it. So taking the fundamental research that we developed during the PhD and trying to make a marketable application out of it, really an application for the better of patients and for society. And then I started doing a postdoc here, and I've been doing that 4 years already. And I'm really happy to also try to make an impact with my research. So not only do the fundamental research, which is of course also impactful, but really transforming it into applications.
Thank you so much for this introduction. Our listeners often ask a question: when you have a background in electrical engineering, how much of neuroscience do you need to learn in order to work in neurotechnologies? How was this in your case?
Yeah, that's a very good question, because engineers, they are often taught the black box principle. So then we try to think about the brain as a black box, and you put a stimulus in and you get a response out, and you try to model it. Most engineers try to model it in a linear way, which is also not often the reality. So indeed, it's not always easy to really understand what is going on in the brain. I think many people still don't know. But as I said earlier, a big advantage of our research group here is that we're very interdisciplinary. So we work together with ENT doctors and audiologists and some experimental psychologists to really work together, find out the best techniques and how to interpret the results that we get out of them.
Yes, so working in the interdisciplinary team really helps because you can learn also from the specialist.
Yes, of course. Yeah. So I can bring a lot of technical knowledge and how algorithms and transfer functions and all those things work. And then they can give interpretations to the signals that we are measuring. And if you see a nice plot where brain areas are lighting up, they can explain that to me. So I think it's really essential almost for this type of research that you work interdisciplinary.
And I'm just curious, what was the topic of your PhD thesis?
During my PhD, I started working on cochlear implants, and the specific problem that I was trying to tackle was to find objective measures for how well someone is understanding speech with their cochlear implants. Because, as you know, a cochlear implant, it tries to restore sounds, and most importantly, makes people listen to speech again and understand speech. But once you're out of the clinic with your implant and the audiologist is no longer next to you, who knows that your implant is performing optimally? And we wanted to make a system that could measure by sensing from the electrodes of the cochlear implant how well the person was performing with their cochlear implant in everyday life. So it would be a monitoring system for speech understanding in everyday life. Of course, we didn't fully complete it during my PhD, but we made some nice essential building blocks for such type of system, and the type of objective measures that came from this research, the objective measures that we developed, they also are now the fundamentals of BCI Award project that we submitted for making a real-time hearing diagnostic system based on brain responses.
Yes, this was my suspicion that it was connected. Yes, so it is.
Yeah.
Yes, so maybe you can talk a little bit more about the outcomes of your PhD thesis so that it would be easier for us to understand how this project developed further already into this BCI Award submission.
So the outcomes of the PhD projects, we mainly focused on two important aspects. So one was developing the objective measures for speech understanding and measuring the cochlear implant users. And the other aspect was really measuring them with the hardware of a cochlear implant. So that's one part is more software-based or algorithms and analysis of the EEG responses that you measure. The other one involved a lot of hardware because you have to imagine the electrodes of a cochlear implant. They are there implanted somewhere in the ear, but they are not designed fully to measure brain responses. They're mainly made to stimulate, but of course, they're in a nice location. They're in the cochlea. If you could measure signals from them, it would be probably a very nice signal quality. But that was not known yet because the hardware doesn't exist yet to measure with an implant. And that's also one of the challenges that we tackled together with some manufacturers of cochlear implant devices. to enable the measurements of those objective measures. So one part was really designing algorithms and measures. The other part was how can we measure this from implanted embedded electronics of clinical devices.
That is amazing. So it's a new way to record signal. Yes. And what was the outcome of this? Were you able to actually develop them? What type of recording did you get? And also, one of my questions is, of course, this is relevant clinically, but also probably you learned something about the brain when recording that information from those electrodes. So maybe you can talk a little bit about that.
One of the biggest challenges that we faced is that when you have a stimulating device, like a cochlear implant, and you record neural signals, then I think most people that listen to this podcast will know, you will have interference, the stimulator and the recording. It's all electrical activity. So it's really challenging to get a nice signal out of it. So one of the outcomes was indeed that we were able to prove that these brain responses to sound that you normally measure in normal hearing persons, that if you try to measure them with a cochlear implant user, you can clean the signal well enough to also get those responses despite the artifacts of the stimulation being present. That was one of our main findings and a new algorithm that we developed. It was very nice. Regarding the measurements, where you try to record from implant electrodes themselves, we didn't really expect that it would be impossible. Of course, we hypothesized it's an electrode that is there. Of course, you can measure from it. But the problem I just explained about artifacts being an interfering factor, they are even more problematic when you're measuring from the implant itself, because of course you're really close to the stimulating device. You're not measuring from the scalp, whereas there's more distance and you can exploit some spatial properties of the signal. So there we really had to be creative and find other solutions to minimize the interference of the artifact. I don't know if it's interesting if I go into detail here, but in the end, we did manage to get recordings that were artifact-free from cochlear implant electrodes. So that was a very nice result because it was the first time ever that this amount of continuous EG in response to speech signals was recorded from an implanted electrode in the cochlea.
Yes, thank you. Looking at that signal, doing those recordings, was there anything that you learned about the nervous system that maybe, we didn't know before that was something new?
I think the research that I just described, it is not really about gaining new fundamental insights to how the hearing system works, but more about enabling new techniques to measure it and really having a proof of concept that all the nice fundamental neuroscience that we know about can be translated to embedded devices with new measurement techniques. So, of course, I'm also not a neuroscientist, but the responses that we measured, we could see very logical things like they have a certain latency. When you have responses from the cortex or the brainstem, there's very different morphologies and different latencies. So we actually used things we already knew about neuroscience to validate that what we were seeing was actually a neural response and not an artifact or a noisy signal.
Yes, yes. So it was more validation. Just sometimes, we get some unexpected things that we learn during the process, and, this can add some information. But yes, you accomplished your main goal. That's very clear, and you validated this device. Yes, so thank you so much for explaining all that. And now, how did you transition from this project to already a project submitted for the BCI Award?
So during my entire PhD project and also other PhD students from this lab, we have worked a lot on really getting objective measures for how well someone can understand speech. Until 10 years ago, this was a really new field. There was not a lot known yet about these type of envelope tracking responses that we use. At the end of my PhD, I started thinking about what do I want to do with my life, my career. I was not so sure I wanted to stay in academia. I wanted to go to industry, but then I don't want to go to work for a big company. I thought more like, it would be really nice if I can take the results from my PhD and start a bit of entrepreneurship with it. So we did a lot of brainstorms, and we also followed courses from the university on research valorization and on entrepreneurship. And we started thinking what can we do with these nice research results? And while originally during my PhD, the research was focused on cochlear implant users, we actually identified some other nice use cases for objective measurements of hearing. So, of course, some of them already exist in clinical practice, but this was really a new technique based on speech responses. And then we came to the current project, which is there's a lot of very young children that have a hearing problem, and they have a lot of difficulties taking tests for evaluating their hearing or how well they understand speech. So what if we take our speech-based tests and try to apply them to those children that might have difficulties at the moment? And we applied for a translational grant to take nice research results and make it into an application. And with that, the first thing we have to do is, of course, a validation or a clinical trial. Can you even do this with young children? And does it work the way we intend to? And that's actually the stage where we are now, that we are running a clinical trial and seeing that our software that we developed actually gives meaningful results, that it is safe, that it is useful for an audiologist that is helping those children.
Yes, thank you so much. Maybe you can tell a little bit more what type of children need help with the objective measurements of hearing. What problems are they experiencing?
Children with hearing loss, there's actually quite a lot of them. Many countries, also in Europe, have very nice newborn hearing screening programs where already some type of neurotechnology is used. So they do a screening based on a brain response to detect whether a sound is being registered in the brain or not. And if the children fail that test, and that is around 100,000 children every year in Europe that fail the test, they get referred for more specialized diagnostics because they failed the hearing screening. So, of course, you want to make sure that there is no problem. And then really the issues begin because you require a lot of expertise and good tools and very good measurement techniques to figure out, okay, this baby here is not hearing properly, but what is the problem? Is it a simple cold and are the ears obstructed, or is it really a fundamental deficit, or did it have an illness or something in the pregnancy go wrong? A lot of information is not yet known by the clinician, and then you can also not start the right treatment. I want to stress that it is, of course, very important for very young children to have access to hearing and to speech at a very early age, because it's crucial to their development of language, to their social skills, to how well they perform in school. There's really a critical window for children to hear and to acquire language and to listen to what their parents say to them. And we have to make sure that they have access to all that richness of sound around them.
Yes, absolutely. And my next question is how this screening is currently being performed. What are the standard ways of measuring the hearing and speech in those little?
So in hearing tests or in audiology tests, there's two very big categories. We call them objective or behavioral tests. So the behavioral tests, they rely on a behavioral response. It's very easy to do with adults. Just make them repeat a sentence or raise your hand when you hear a beep. With very young children, it's very difficult because, of course, you cannot ask a baby of 1 year old to repeat a sentence. Usually, it's very reflex based, or you play a loud sound and then you see do they respond to it or not. You can get an indication, but it's not very accurate. You cannot get a threshold or a level or estimate speech understanding. So that's why objective tests are very important. So objective tests, you don't need any behavior. You can just measure it without even needing the consent of the child. At the moment, these screening technologies, they are based on evoked responses. So I guess most people know that it's just averaging many presentations of the same sound. And this is what in most countries the screening is based on. So you play a click, you play it 30 times per second, and then those 30 times per second times 100 trials, you average it over many, many seconds and many presentations, and you get a response in the brainstem. And when the response is there, you can see, okay, the person has a brain response to the sound, so probably they will hear it. It reaches the brain. If it is absent, then you fail the screening and you get referred to more specialized diagnostics. I think in Belgium, you get a second screening to see if the first screening was just a fluke or if it failed. And if the second screening fails, then you really get referred to a specialist to figure out why the screenings failed. But from what I just explained, the testing, it's very good that it is objective because the child cannot interfere or does not have to do anything. But it's still a very rudimentary technique, these evoked responses. You just get an on-off response. Is it there or not? Sometimes in diagnostics, you can go a bit more into detail by varying the loudness of the stimulus that you present. So you can try to estimate a threshold. But still, this threshold estimation, it can help you estimate what is the degree of hearing loss, but it still is a very peripheral, low-level process in the brain that does not predict very well speech understanding or language development later on.
Yes. So how did you propose to solve this problem? What approach did you propose to develop?
So our technique is not based on event-related potentials that you have to average, where you have a lot of presentations that you have to average, but we really use a natural speech signal. And with natural speech, I really mean like a real story that is narrated or like an animated movie. And because sometimes people say we use speech, but then they use vowels or individual phonemes, which is more speech-like, but it's not real speech. So we present a story, it's a narrator, the speech fluctuates in loudness, that gives an envelope to the amplitude fluctuations. And that envelope of the natural speech signal can be decoded from brain responses with machine learning techniques. There's many different techniques that you can use. We mainly now focus on one of the simplest linear techniques that you can use. But the presence of this envelope response in the brain, we have shown that this corresponds really well with speech intelligibility of children and adults later on. So here we have for the first time an objective measure that not only measures does the sound go through, but is speech being processed properly like it should be. Because sometimes you have people that have a normal brainstem response, but not a normal response to speech. So this is actually a way to differentiate these higher level cognitive processes that are required in the human brain to process speech and to understand it are present. And the very cool thing is that these mechanisms for tracking envelopes of speech are already present from the moment they are born. And of course, we're not going to say the baby understands speech when it's present, this response is present, but the normal mechanisms for developing speech and language skills later on are already present in this infant. And this is a very important differentiator or a very important technique to be able to measure this when the child is still very young and differentiate between different problems that might occur.
Mhm. Thank you. You already described how the standard conventional evoked responses are being measured. So usually it's amplitude of the response, presence of the response, latency. What measures are you using when you are evaluating this response to the speech envelope? What is it that you get by using machine learning? Maybe you can describe more in detail.
Of course. So what we actually do is we train a machine learning model on the relationship between the speech and the brain signals. So we feed it EEG signals where we know what was the stimulus that we presented. So it tries to learn the relationship between the stimulus and the EEG signals. And then we give it a piece of EEG signal where the machine learning algorithm does not know what the stimulus was. So we ask the machine learning algorithm to reconstruct or decode an envelope of the stimulus. And then we look at the ground truth, what was actually the real stimulus that we presented, and we can compare it to what the algorithm thinks was the decoded envelope. And when there is a high correspondence between what we can decode from the brain and what was actually heard, then we say, okay, this person is processing this information well because we can reconstruct it quite accurately. If there's no correlation or no correspondence, then we say, okay, these mechanisms are disturbed. There is no neural tracking this envelope. So these types of correlations are what we look at. So the quality of the decoding of the envelope. But I also want to add that we're not only looking at envelopes, because envelope responses are one of the most robust features that you can use. But you can also use other representations of the stimulus. For example, you can use a phoneme segmentation and try to decode individual phoneme categories, or actually individual phonemes. And you can also use spectrogram representation to have more fine frequency specific information to see, okay, we can decode certain frequencies, but others not. And that might have also some diagnostic or rehabilitation that might also have some implications for the tuning of the hearing aid or the hearing implant that you give them, depending on what frequencies they hear or not. The most easy feature to use is the envelope, and we use that. That's quite robust, but there's a lot of different features that you can use. And this combined model of all these correlations and all these features that are being processed in the brain, this is what we are employing now as a new clinical methodology for getting to diagnostics for the processing of speech in the brain.
Mhm. Very interesting. And now this corresponds between the brain response and the actual envelope, yes, that you have. How do you determine the degree of that correspondence that is equal to, or that you may be labeling as healthy processing, or the processing with maybe already some challenges associated with some challenges? So how do you make the determination what is still in the healthy category and what might be already a pathology?
So that's a very interesting clinical question that we also often get from audiologists and doctors. And that's exactly also the question that we're now trying to answer with our clinical trial. You might say that you can either detect let's say an envelope following response, or you don't detect it. So you have a binary decision, it is there or not. And we apply a lot of statistics to make sure that it is very robust, that it is not a false positive or a false negative. So with that decision, the binary decision, we actually do it at many different intensities. So you can look for these envelope responses in a challenging hearing condition, like there's a lot of noise or it is very quiet. You can do it in a very easy listening condition and everything in between. And then you can get a curve of the probability that a response is being detected and how significant this response is. And based on this curve, you can try to estimate what is actually the threshold, or what is the amount of difficulty in listening that someone can tolerate before their envelope tracking responses start to disappear. And this is a very important clinical measure, determining this threshold at which only 50% of the speech can be understood, or maybe 0 or 100%. And from that curve, you can already get a lot of information about the degree and the type of hearing loss of patient.
Thank you. And very often when we are developing a new technique, we want to compare it with a certain ground truth, at least the ground truth that currently exist in the field. Is there any ground truth that you are comparing the outcomes of your studies at the moment? And if so, what results do you get when you compare?
This is very challenging to find a ground truth for babies and to assess how well they can hear, because usually you have to wait until they are old enough and see, oh, actually they didn't hear a lot, or they did hear properly when they were a child. We try to solve this problem by very systematically reducing the age of the children that we are evaluating. So we started with doing studies on children that are 5 to 6 years old, and they are in the age range where you can ask them to do a behavioral test and behaviorally verify that they can repeat words and hear sounds. And then try to also do objective tests in that population and compare the behavioral and the objective tests. This is also published in some papers. We found a very nice correlation between the behavioral and the objective results. So we thought, okay, this is nice. We can predict the behavioral outcomes from the objective ones. Let's now reduce the age and go to younger children, where the behavioral measures start getting shaky or very difficult to do. They have less accuracy. And use the evidence that we found from children that are just a bit older to see, okay, when it is valid for these children of 5 or 6 years old, and we can find very robust objective responses in these somewhat younger children, we will assume that this is a good predictor of the real speech understanding that they have. But for really getting a ground truth for that population of younger children, I don't think it exists. We use some approximate behavioral measures, like their estimated audiograms based on the expertise of the audiologist that observes them and does these kind of reflex tests where they clap and then see whether the child responds. But it's not a very accurate ground truth. So it's also very difficult to correlate with, because you don't know if you make that correlation, is my objective measure wrong or is the ground truth of the behavioral measure wrong, because it's very inaccurate.
Yes, yeah, it makes sense. My next question is, and this is the question that actually many people are asking when there are studies with the young children. How do you work with young children? What approaches do you use? Especially, you go through different age ranges, and children are differently active during all those times. And so, your approach to working with young children, how do you do it?
Yeah, it's for sure a lot more challenging than working with adults who can sit still for multiple hours. I'm also not the expert on doing the measurement with children. As I said earlier, we have an interdisciplinary team. We have also a very good audiologist in our team that's very experienced with testing with children. And to make it more bearable and tolerable for the children, we did a lot of adaptations to our protocol to make it as child-friendly as possible. So, of course, you cannot make it too long. So you really have to pick your conditions well and make sure it never exceeds half an hour. We also made some technology choices for the EG systems that we use to not have a system that requires very long application time, because of course, when you have to inject gel for 15 minutes and the child has to sit still, it is already agitated or bored before the test even begins. So we opted for a system with wet sponge electrodes. So you just soak it and then you put it on the head and it's actually already ready to go in under a minute. So that's very important. And another thing that also my team member, the audiologist, does very well is really making the child feel at ease. You use a lot of toys and nice figures, and you explain to them what's going to happen if it's old enough, to make sure that they are not scared by having the cap put on, and that they're not scared by having to go sit in front of a screen and watch a movie. It's actually very funny. We have a very big teddy bear that we use to put on a dummy of the electrodes head cap, so that the child can see, oh, this bear is looking friendly and it can tolerate putting on the cap. So then it's less scary for the child, because then they also want to put on a cap like the bear. But it's a lot of these types of strategies that you have to employ to really make the child feel happy and at ease and make them happy to do the test. Maybe one more I think it's a very nice advantage of our test is that, as opposed to using these very boring click sounds or tones that are being repeated all the time, an implicit advantage of our stimulus is that it is natural speech. It is a narrated story. Actually, in our latest protocol, we are using the audio of an animated movie with a lot of voices. So the child can actually watch the movie, and the children, they love watching movies and sitting in front of the screen. For them, it's just like going to the cinema. They don't even know that they're undergoing a test, besides having on a weird cap. And that stimulus that engages them also is the stimulus that we're interested in. So it's a very nice match and very appropriate to apply this technique in young children.
Yes, that's a great approach. And similar approaches are being used in fMRI scanners. There's like a Max scanner where children can put their toy and see that everything is good. Nothing happens and the toy feels good.
Yeah, of course. Yeah. I'm not claiming we invented these techniques, but I do think we're also very lucky that we have nice people here that are very experienced with testing children, and that can get nice EG data from children, because not all children are very easy to measure. So it's a challenge, but it requires a lot of experience and expertise. But so far, it's been going quite well.
Yes, that's true. But actually, it's the first time I heard about putting a cap on teddy bear or a toy and application it with the children. So that's very interesting point. Thank you. And my next question is, what are the
biggest challenges in the methodology? Yes, we already talked, of course, it's a young age of children. It's already a big topic on its own. Anything else that you find challenging in this approach?
So if you're doing brain research with children, I think one of the biggest challenges, and also you get a lot of criticism for that, is that, of course, there's a lot of maturation and plasticity still going on in very young children. So you either need to pick a very select age range of children, but even that is not so easy because children mature at a different speed, and especially some children, they start to speak earlier than others. So their hearing and language maturation might be very different, even when they have the same biological age. So yeah, that's a big challenge. And we have usually a range of 1 to 2 years across the children that we test in our studies. It's actually not appropriate to start taking group level results and grouping the youngest children in an average together with the oldest children. You really have to do your analysis and the diagnostic that you try to get on a subject specific level. Of course, if you start working with subject specific data, then you need to collect enough data, so you cannot do a lot of conditions. So I think that's a big challenge, like trying to take into account the individual responses and taking into account that not any child is the same as another child in your cohort. Of course, being forced to do subject-specific analytics is not bad because we are trying to go for an individualized diagnostic test. So being forced to think creatively about how we're going to solve these issues is actually a bit of I'm not going to say an advantage, but it's the direction that we want to go in. And the challenges that we solve, they're actually really important to develop the medical device or the application that we're trying to develop.
Yes, I absolutely agree. And taking the fact that you are taking into account the neurodiversity, that each brain matures at its own speed, at its own time, and developing those individual approaches, I think is very, very important. So I'm glad to hear that you are doing this. How many electrodes are you currently using in your study for EEG?
That's a question we also get very often, especially if you try to transition to a clinical application. Then the fewer electrodes is always better in the eyes of the clinician because they think they have to stick them all on individually. But of course, it also makes it more expensive if you need many electrodes. Our fundamental research, we did it with 64 electrodes head caps, but that's way too much for the application that we are using it for. But of course, in research, it's nice to have all the electrodes, the full scalp. You have a lot of redundancy and try to pick and choose which electrodes are the most important for this type of response that we're looking for. Now we transitioned for our clinical trials to a cap with 24 electrodes, but we are actually planning to move towards 8 electrodes. But the 8 electrodes, it's really a result of a lot of studies and optimization about where do they really have to be placed in order to really measure the responses that we want to get. So I would advise anyone to start with a lot of electrodes, and when you really go to the application, know which ones are really important and then reduce to a smaller amount. But I would never start this type of research with trying to buy a small headband or a few electrodes and then hoping that you capture the right response.
Yes, very good suggestion. Thank you. And what were the results of your study before you went to clinical trials? So I'm just trying to understand what was already established, what was that minimal base that you needed to start your clinical trial?
Of course, I cannot take credit for all the science that happened before because in our lab, even before I started, a lot of people were doing research on adults and their speech processing. So there was a lot of knowledge about you put an adult in front of a speech stimulus, you vary the level or the noise of the speech intensity, and then you can characterize how the responses to the different features change. Then we came in with our project and we really started applying these techniques on children with all the challenges that you have with testing children. But then we found, okay, we now tested, let's say, 20 children in our lab. At first, you go to normal hearing children, then you do 10 more children that have a hearing deficit. So you start making your populations more and more challenging, going from adults to children to hearing impaired children. And then at that point, we saw, okay, with these hearing impaired children that we test, we have very nice results in a lab setting. This is very promising for an application. So with this exact protocol, we want to do now a clinical trial. And this trial is basically repeating what we did in the lab, but on a much bigger scale and also in a realistic clinical setting. So our tests in the clinic, they are not happening in a Faraday shielded cage. So you need good, this is an extra validation of whether the response is robust or not, because not every hospital has a electromagnetically shielded cage. And another big difference of transitioning to what we established with children in the lab and going to the clinical trial is that we are no longer the ones taking the test. So it's not us running our scripts and our software and knowing what is the next condition. We really have to make software that a clinician can use. And it's actually really underestimated, or maybe not underestimated, but we really put a lot of time into making it user-friendly, and this button does that, and it's very intuitive and obvious how the protocol should be run. I think that's a big challenge of transitioning to a clinical trial, to really make it user-proof or user-friendly.
Yes, I think that's such an important topic, this distinction between the research in the lab and the clinical trial. Do you think you can maybe summarize the main points of difference between one and another, like the major points?
So the main difference between doing the tests in the lab and the clinical trial, from my head now, I can say there's two very important aspects. So one is the control and the confounds that you can reduce. So in a lab, everything is very controlled. It's very clean environment. You always have the same researcher doing the same protocol. And that you don't have that in a clinical trial, where the patient is very different at a different time of the day, and the researcher might be very different, and you don't have all the equipment that you have in the lab. And the second important aspect is that it's not the researcher doing the experiment, but the clinician doing the experiment. And the researcher has very clearly in his mind, I designed this protocol, I know what is the next condition, and this is what I'm going to do. And the clinician is just a user of your software. They got some instructions to apply this test, but they are not an expert. They might make errors. They don't know how to operate the software. They might not even have experience with putting on an EG cap. So how do you design your experiment that it's robust to that type of errors or inaccuracies? I think that's the main differences between the testing in a lab or in a clinical setting.
And how did you make this software or this testing protocol user-friendly so that clinicians can use it? What were the main problems that you addressed to ensure that it is user-friendly?
So one part of the user friendliness is actually mandated by regulatory requirements. So you have a lot of checklists and things that you have to prepare for a clinical trial, like making sure that there's a very extensive manual, that there is a tracker for issues when someone has a problem with the software, so that you can fix it if something is not clear or not working properly. You have to make screenshots of all your program interfaces and explain with arrows, this is how it works. So by following those manuals, you already get somewhere. But of course, designing a user interface, it also requires a lot of experience and testing. So we actually have another team member that was also an engineer and is now programming a lot on our software and has becoming very good at it. And the manuals and the things that you developed, it's very important to the person that is developing the software to frequently check with the user how they are experiencing the software. So this is also something that we do during our studies when there's feedback about, okay, I get this graph out of the software, but I don't fully understand it, or can you scale it a bit differently? Because to me, it's not very clear. Things that for us as a researcher are very obvious because we have been working with these types of graphs and these techniques for many years. And then a new person looks at it and it's not intuitive. So yeah, it's very important to always take into account the feedback from people that are actually using it and don't have the same level of experience as you.
Thank you. my next question is, what was the biggest challenge for you in this clinical trial, and how are you solving it?
I think we had many challenges for setting up the clinical trial, and it's a lot of different things. It goes from things like just finding funding for a clinical trial, because a clinical trial is expensive and you have to reimburse patients and clinicians that are taking time out of their clinical workflow to implement your techniques. And yeah, that's a big challenge. Another challenge is for sure the regulatory part, that it takes very long to get approved and to have all the documents and administration ready before you can even begin. And it goes through many audits, and that also costs money because you have to pay an auditor to look at your files and tell you that they are okay. I think maybe with the design of the protocol, we didn't have the biggest issues because we already were very well prepared from a scientific perspective, and we already ran the protocol before. So that's not really where the challenges were. It's more, all the practicalities and the funding surrounding clinical trials. I think that would be the biggest challenge.
How was the learning curve for you to learn all this new protocol standards and everything that you need to prepare for clinical trial?
Yeah, the learning curve was quite steep because I think most researchers, when they're doing a PhD, they're not too much concerned with all this documentation. You usually have some ethical commission and they approve your study, and then they have some comments, but it's not that much work. And then you suddenly say, I want to do a clinical trial. And then especially when you say, I want to do a clinical trial on children, all the alarm bells at the regulatory office going off because, it's a lot of risk because it's children, even though you're just putting an EG cap on their head and putting them in front of a movie. When you start this process, you get an entire folder of documents and there's hundreds of pages that you have to fill out, and you see it and you're very intimidated by it. It's not very difficult work, but it's a lot of work, and it's important that you do it very precise and meticulously. I think, again, in my team, I'm very blessed to have had colleagues that work very meticulously and that are good at learning these things. Everyone had their share in preparing the documentation, but you really have to tackle it as a team and just work your way through and take time to do it because it takes a lot of time.
Yes, absolutely. It does. My next question is, do you already have some preliminary results that you can share if you have them?
For the clinical trial, it is unfortunately confidential, so I cannot share any intermediate results. But I can say that the clinical trial will end by the end of 2024, and then we can make a publication or an announcement about the results. And hopefully people will find it interesting, and hopefully it will be favorable results for the technology that we're developing.
Absolutely. And we will be happy to welcome you again on our podcast to talk about those results.
Yeah.
What about the results that preceded your clinical trials, just to bring it to an end from the start to at least the point when we can talk about the results?
Yeah, so right before we started our clinical trial, we published some papers about our work in the lab in children, both with and without hearing impairments. And those results, they are published. I can talk about them, of course. A first paper, it's actually following the methodology a bit that I talked about earlier. You start with a somewhat easier population, like older children with normal hearing, and there you can really nicely compare their objective results with the behavioral results that you can measure in these children. That was a nice correlation, so nice validation of this technology. Then you go to the hearing impaired children. There we also wrote a paper about the neuroscience of processing speech as a child with a hearing aid. We found, actually that individually, each of these children with hearing aids showed very nice responses to the sounds that they were hearing during the experiment. And actually, you could even see, so something interesting that we did with these children is that we tested them both aided and unaided. So they took the test while they were wearing a hearing aid and while they took it off. When you look at the result for these children with or without the hearing aids, and you do this test at different challenging listening conditions or easier listening conditions, you can actually see at what point, the hearing aid is providing an advantage to them. So, for example, you can see that in the very challenging listening condition where the sound is very soft, the hearing aid gives a normal brain response, whereas if they take it off, it is not there. And at the easiest listening conditions, they have a response even when they're not wearing the hearing aid, because it's, for example, a sound at 60 decibels, but they have a hearing loss of 30 decibels. So, of course, they still more softly, but they still hear the sound that they're supposed to hear. So this is very interesting because you can pinpoint what is actually the threshold at what point the hearing aid starts performing well and starts giving an advantage or not. And you can also see, of course, what is the level of hearing loss that they have from these types of curves.
Yes. So that was the second study. Yes, the first was with adults, you mentioned, then the second.
Yeah. So now I'm really talking about the project with children. And so beforehand, there was a lot of research with adults. And then we went to the first study, I considered the normal hearing children. The second study is when we start looking at hearing impaired children. And then we did another study later, which is not yet published, but the results have already been presented at some conferences, where we really go to infants and babies younger than 2 years old and also try to make predictions about their level of speech understanding or what they will develop later on based on their neural tracking responses, which we can measure in these babies and infants that don't understand speech yet, but their brains have the capability of tracking speech features. So that is required or a necessary condition for developing speech and language later on.
Thank you so much. Fascinating studies, and looking forward to the end of your clinical trials and learning about the results. Is there anything else that maybe I didn't ask you and you still want to mention about this project?
So yeah, actually, it's even in the title of our project. It's a real-time system that we developed. So maybe that's also a nice progression that we made. Before we started the children projects, this was just offline analysis. So you let an adult watch movies and listen to sound, and then afterwards you analyze the results. But when we transitioned to the children studies, we actually made a real-time interface so that you can see during the experiment whether the tracking of the features that you want to see in the brain, whether they are developing and whether your experiment is going well. And this is actually also very interesting towards the future because it can make the testing protocols more adaptive. You don't have to have a fixed, let's say, 10 minutes of recording of one condition when you only need 3 minutes to get to a significant response at that certain condition. And then you can quickly move on to the next one and shorten your clinical protocol. So that's why we think it's a very big advantage for this technique to have also developed it as a real-time system so that you can know whether the experiment is going well, whether the measures are significant at a reasonable time. There's a lot of clinical applications.
Yes, yes, and thank you for mentioning that the real-time component. It's really very important. And I just got very curious. So this is my question. You are using natural speech as your stimulus. Why did you decide to use natural speech? Because you can still extract all the frequencies of the speech and put it in a sound envelope, yes, that will contain all the frequencies. In this case, it wouldn't have the semantic component. So you would know that definitely a person can discriminate or his brain can respond to all those frequencies, but semantics here is not so necessary because you are working with small children. So I'm just curious why the decision was made towards specifically just natural speech as the main stimulus.
So actually, we are very interested in natural speech because we consider it the most ecologically valid stimulus. This is actually what we are trying to restore by giving people hearing aids or hearing implants. You really want them to have the best access possible to speech and that it is understandable. You don't want them to hear beeps and sounds or individual letters the best. You want them to hear speech the best. So that's why we think it's appropriate to use this as a stimulus. And if it works with this as a stimulus, it is, I think, the best proof to validate that this hearing aid is working properly for them. you make a valid point that you can say, okay, you can make artificial stimuli that contain the same information as some speech signals. That's true. I don't fully agree. If you really want to test acoustics, that is true. You can look at very peripheral responses to modulated envelopes. But what you said, that you can also evaluate semantics and like word and phrase level features. I think that's something very important about this technology. When I talked earlier about we try to decode envelopes, envelopes are just one feature that you can try to decode from brain responses. And we actually have an entire set of features going from very basic acoustic envelopes to frequency-specific envelopes to individual phonemes to semantical features, linguistic features that indicate some sort of surprisal when you hear a certain word. And all of these features, they are corresponding to the hierarchical pathway of the brain. So actually first acoustic information is being processed, then you have segmentation of words, then you start mapping words to meaning, you start constructing sentences and concepts in your brain. And by using all of these different features, which you only have with the natural speech signal, you can actually start to differentiate between, for example, a child that can hear an envelope but doesn't hear it in the right quality, or it hears the envelope, it hears the sounds, but it doesn't understand what is being said. For example, an auditory processing disorder, versus a child that really has a hearing loss and doesn't hear anything. You really need to have a different therapy or rehabilitation for these children. And by looking at different stages of processing in their brain based on natural speech, you can also give them what they need in terms of rehabilitation.
Yes. So do I understand correctly that having this natural speech, you also can decompose the response into those different levels of processing, including and separate, let's say, semantics from the processing of sound?
Yeah. So there is already scientific evidence that also semantic and linguistic, very complex features, that you're able to decode them from brain signals. And then, if you want to visualize what the type of feature looks like, so an envelope everyone can imagine, but you can also have a time signal where the height of the signal relates to how surprising the word is in a sentence. So when you say, for example, at my house, my pet is and then you might expect dog or cat as the next logical conclusion. But if you have, for example, turtle, that's a bit more surprising. Or even if you say tree, that doesn't make sense. So there you have a very different structure in the meaning of the word in a sentence. And when you construct such features, you can also decode them from brain signals and get relevant information about, does this person have problems mapping meaning to words and mapping surprisal values to certain words?
Yes. Do I also understand correctly that you constructed those sentences in such a way that you can decode those various stages of processing?
No, so at the moment, we are using the audio that goes with an animated movie with a lot of voices. It's not a specifically constructed artificial sentence. That's our entire point, that we're just using everyday natural speech, which is very relevant for a child because they might watch a lot of movies. And you can calculate these features, like these existing sentences. You can run it through an automated model that transcribes it to phonemes, to individual text tokens, and then couple with a language model, couple some surprisal values or information values to them. And that's the type of features that we use in our research.
Thank you. Very interesting. So thank you very much for all this information. Really exciting and looking forward to the developments. And I would like to talk a little bit about your career now, as our podcast is all about neuro careers. One thing that you mentioned that really interested me is that you didn't want to work just in academia with basic research. Yes, you wanted to have an industry exposure, and you found this happy medium, yes, where you can still work in academic settings, but conducting clinical trials, still connected to the people who work with you in the lab and develop certain products that might be and will become commercially viable. So why is that? So why Why wasn't it enough for you? Yes, just to be in academia. Why did you want to have this industry component?
Yeah, it was not necessarily the industry component, but more the entrepreneurial component, like really having a lot of ownership over your project and or your company and creating something that helps people, but also helps yourself because you can employ yourself and you can really try to build something that you can be proud of. Of course, in academia, you also do things that have impact and that you can be proud of. But if you look at the career path, I think if you stay in academia, often you end up trying to become a professor or try to start a research group. I have a lot of respect for that, but I don't think I would do it myself. I really wanted to the industry in the real world with companies and applications. I developed some interest as well for economics and for starting businesses and trying to make a business plan for this type of technology when it's actually is ready to go to the market. So that's a bit more of, for me, that's a more tangible way of creating impact with what I researched during my years in academia.
Yeah, and that's also a very interesting and important point, how you can transform the work that you've done during your PhD studies, your studies in academia, into your own entrepreneurial venture in a way, which, many people also are curious about how they should approach their own PhD work. Yes, so if you have certain idea, you can develop it and then you can transition into the entrepreneurial venture.
But I think as research, we always have to apply for grants and we have to explain to governments and to granting bodies like, oh, this research is so important because look how many patients there are and how much impact and look why you have to fund us. And I think those are the same problems where there is also a business opportunity because you are doing research to solve problems. That's actually your job as a researcher, to understand and to develop science to solve problems. So I think it's actually quite natural to, at the end of your research, to think, okay, I did some nice studies. Can I solve a real problem with this? And if if the answer is no, of course, do more research and try to solve the problem. But usually you end up with a technology that has some kind of needs or can help a patient. And it's logical to say, okay, let's build it into a product and make a business or sell it or license it to a bigger company that can use it. So, yeah, I think it's not really far-fetched to try to make a commercial strategy at the end of a research project or developing something.
And what was the knowledge or skills that you needed to acquire in addition to what you had already in order to start this entrepreneurial path?
Yeah, that's also a very good question because me and I think a lot of researchers are really not very entrepreneurial minded. We're actually usually a bit the opposite, like very perfectionistic, very driven by really getting to the bottom and getting every outlier and edge case explained. Whereas if you want to make a product and go forward and go quickly, then it's all about quickly making a prototype, testing, improving, and just going when it's good enough and not really focusing too much on the details. So that's a bit of a change in mindset. And to be honest, I still sometimes feel like I struggle with it to not get lost in the details and just go ahead with it. Regarding skills, yeah, for a large part, I think you can learn about entrepreneurship. Some people have a talent for it, but you can take a lot of courses, learn how businesses work, learn how to negotiate, how to set a price, how to develop a product or follow a regulatory trajectory. So that's also something that I did myself. I followed during my postdoc also a business education. I'm very happy that I did it because I came from almost zero and now I'm not an expert, but I think I know enough to know the basics of how a company works and how you make a financial plan. So it's definitely achievable if you want to learn and you're passionate about your project. I think that's the most important thing, that you just want to learn and that you really are passionate about the technology that you are developing.
Thank you very much. And what would be your advice, recommendation to those who are going into, let's say, their PhD with the goal of developing their own product after they finish their PhD on this subject?
Yeah, it depends a lot on what type of product is that you want to develop it. Because if you have a really good idea for a product already, then I would say don't do a PhD, but just try to build a company and try to get funding and just go for that. But many products, they require more research and more understanding. And then it's maybe logical to either go to a research group and say, hey, do you already have nice results about this technology that I can try to commercialize? And if it doesn't exist yet and you're really passionate about science, then okay, start doing your own research and find a research group that wants to help you to do it. Yeah, I don't think you should start a PhD just for the purpose of hoping you will find results that you can later commercialize, because at the start, you will never know what is going to be the outcome, or you might have a negative result at the end of your PhD, and then, maybe it's not wasted time, but maybe for you personally, it's wasted time that you really hoped to make a business opportunity out of it.
Yep. Thank you. And anything else you maybe want to add for our listeners about becoming an entrepreneur?
Yeah, I actually forgot to mention one super important thing, and that is that I think for most of the startups or most of the business ideas, you really cannot do it alone. And I also am not doing it alone. I have a really nice complementary, strong team. As I talked earlier, it's audiologists and programmer, engineer. It's like all together, and you really need this. So if you're coming to the end of a nice project and you think, okay, there's some business idea in this, regardless of how strong the technology and how good your business model is, you also always have to look for people that share your vision on this or that have complementary skills to you, to also form a strong team around you and make it work. Because I don't think you can ever, maybe some people can do it, maybe very rarely, but usually you need more than one person to do all of this work, and also to just give you feedback and be your sounding board when you have problems, or try to come to solutions together. So find a team.
Yeah, thank you very much. That's a great suggestion. And I would like to talk a little bit about the BCI Award submission. Why did you submit your work for BCI Award? Why were you interested in this opportunity?
So the BCI Award was not unknown to us from our research group. There has been previous submissions, so we already knew about it, and we knew that it's a nice opportunity to showcase your work and to it's a competition. So if you make it to the short list of the nominees, then that's prestige to your project, and that's always very nice to get some recognition from other people internationally. So I think that was the main driver. Like, okay, there is this competition. It's with very prestigious projects. If we can get on that list, it would be very nice visibility for our projects. Then you have to write an application, like you make a video and a short description of your project. But if you have done a bit of science communication and some courses on writing, which every researcher has taken, then the application process is not too horrible to do. It's actually a very good impact to effort ratio to try to join the BCI Award, at least for us. Yeah.
Thank you. And what do you think made your submission successful, that your project was nominated for the BCI Award?
Well, I think we as a team, we are very passionate about it, and we think it really has an impact. We put the patients or the people that we're trying to help first, and we're developing science for them. So I think that is maybe something that shines through a bit in an application, when you really see like, okay, this is impactful. They're trying to help people. It's something that I saw in a lot of the nominated projects for the BCI Award, that it's really impressive things about re-enabling people to speak or to walk or to measure certain things that could not be measured before. That really opens possibilities for patients around the world. That wow factor that you have in the project, like, wow, they're really helping people with cool technology. Maybe that's, if I were a jury member, I think that would be something that I would look forward to. Yeah.
Yes, absolutely. And what would be your recommendations to those who are considering their first submission for the BCI Award?
Recommendation, yeah. Well, don't do it if you don't really have a lot of results yet. But if you start to get some promising results and you have some papers, and I think most people that apply for this award, they are usually engineers, or maybe not all of them, but I think a lot of engineers, they can really be impressed by cool technology and have a bit of that nerdiness, like, wow, like you can really do this with people and with technology. And if it has a bit of a wow factor and you have some nice results, then just try to submit it. And it's also okay to be a bit of a dreamer in your application and say like, okay, I have some results, but this might imply that we can do these amazing things in the future and have a bit of a future perspective. Then really try to play it out. Like, it's the same for us. We are not yet there. We don't have a medical device yet that helps these children, but it's our vision. And you also try to sell that vision a bit in your application. And then I think it will go well if you try to paint the big picture and be very excited about what you're doing.
Yeah, absolutely. And we have some people who submitted for a while they were developing the project. And at some point, the results were already visible, not the final, but results that are ready to be spoken about.
Mhm.
They received, of course, and nominations and even awards. So it's okay to start even early in the process and to communicate that vision,
Yeah.
and then step by step to get to that point when.
And if it's too early, you could always try again the next year. Right? So there's nothing lost with trying.
Yeah, absolutely. Thank you very much for all those suggestions. And as we're nearing the end of our podcast, maybe you can give your advice to our listeners overall who are seeking careers in neurotechnologies. Anything you would like to mention?
I don't know if I'm the best person to give advice, because I also just followed my interest and I rolled from one thing into another. But maybe that's a bit indicative of what the neurotech career system looks like, because it's a field with a lot of opportunities. It will only get better and bigger, I think, because neurotechnology really is the future. Devices and hardware are getting better, but also software and AI and everything is getting more optimized and better. There will be a lot of new career opportunities. I think just try to look at some projects that you think are interesting and cool, and connect to people and try to follow whatever you think is interesting, whether it's really fundamental science or a startup or a business, or even some people find joy in working a regulatory job in clinical trials or whatever. So there's a lot of possibilities in neurotechnology.
Yeah, thank you very much. It was a pleasure talking to you. Of course, all possible best wishes with your clinical trial, and looking forward to your updates. So thank you so much.
Thank you very much for the invitation. I will definitely give some updates when they are available, and if it might be interesting to you. Yeah.
Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com, or find the link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you're looking for more guidance on succeeding in neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.